Hello everybody, this is it, the last lesson, the last time you have to sit through one of these videos from me. And in this last lesson we are looking at log functions. So a log function is in the form y equals the log base b of a, something like that, where there aren't any restrictions for y, but there are going to be restrictions for b and for a. Now we've talked about not being able to take the log of a negative number or 0, so a can't be a negative number or 0, and that's going to be true for the base as well. So the base cannot be a negative number. It also cannot be 0, and then it also cannot be a 1, because remember the base of the log is the same as the base of an exponent here. If I put this in exponential form, b to the y power equals a, and in order for it to be exponential, that base can't be 0 or 1. So we have similar restrictions with our logs and our exponentials, and actually some more connections which we'll see toward the end. But I want you to see what a log function is going to look like on a graph. And I know we have technology that graphs for us, but we're going to graph this the old-fashioned way. We're going to make a table so we can see what's happening, okay? So for the first one, if we wanted to graph y equals a log base 2 of x, it's hard to look at it in log form. So if I was going to graph that function, I would think about it in exponential form. In exponential form, this would be 2 to the y power equals x, where instead of picking values for x, it'd be easier to pick values for y and see what happens for x. If I put in, let's say, a negative 2 for y, then 2 to the negative second power is going to give me 1/4. If I put in a negative 1 for y, I'm going to get a 1/2. Put in a 0 y, anything to the power of 0 is going to be 1. Put in a 1, 2 to the first is 2, and then put in a 2, and 2 squared is going to make 4. Okay? So at 1/4 on the x, we're going to be down at negative 2. At 1/2 on the x, we're going to be down at negative 1. At 1 on the x, we're going to be at 0. And then at 2, 1, we have a point. At 4, 2, we have a point. If I put in 3, we'd have 8. So at 8, 3, we'd have a point. And what's going to happen is the y values get bigger. These are going to get bigger too. So the graph is going to continue to grow in this direction. And what's going to happen in the other direction? So what happens to the x values here is the fraction gets smaller and smaller, but that x value won't be able to get to 0. So what we're going to see is very similar to what we saw with the exponentials. It's just a reflection of the graph we had before, just a different kind of reflection. So there's our 2 to the y power equals x, or log base 2 of x. If we make that a 3, hopefully you already know what's going to happen here, but if we were looking at 3 to the y power equal to x, and I put in negative 2, negative 1, 0, 1, and 2, then 3 to the negative 2 would be 1/9, 3 to the negative 1 would be 1/3, 3 to the 0 is 1, 3 to the first is 3, 3 squared is going to make 9. So this side of the graph is going to look pretty similar. At 1/9, we're down here. Well, I don't know, you're not going to be able to tell the difference between these. 1/3, we're at negative 1. This is the same exact point. But then 3, 1, and 9, 2. And so this part of the graph looks pretty similar, but it's flattened out here a little bit. So this was the log base 3 of x. And this one was the log base 2 of x. Okay. And we got one last one here just so you can compare. Oops, just so you can compare. So if we had 1/2 to the y power equal to x. So if I put in a negative 2 here, then we're going to end up with negative 1/2 to the negative 2, or 1/2 to the negative 2 would be 2 over 1 to the positive 2. That's 2 squared, or 4. This is the reverse of what we were doing 2 days ago. Hopefully it's looking familiar. Put in a negative 1, we get 2. Anything to the 0 is 1. Anything to the first is itself, and then 1/2 squared is going to be 1/4. So at 4 on the x, our graph is at at 4, sorry, our graph is at negative 2. At 2, our graph is at negative 1. 1, 0 again, and then 1/2 and 1. And 1/4 and 2. So we can see the reflection happening here, just like we saw the other day. So these graphs look pretty similar to what we had the other day. This was like log equals 1/2, log base 1/2 to the x, or of x, I'm sorry. So similar to what we had the other day. See, the other day, if you remember, we had these exponential growth functions that look like this, and then if we made the base a fraction, then it reflected the graph. The same thing's happening here. It's just happening with the x-axis. So we had a log growth function that looked like this, and then we reflected it and made it a log decay function like that. Okay, so we have the symmetry happening about the x-axis instead of the y-axis. But this is generally what's going to be taking shape when you graph a log function. So instead of having the horizontal asymptote, you have a vertical asymptote. You still have some similar characteristics where it looks similar in shape to the exponentials, but again, the symmetry is happening with respect to the x-axis. So all of these have some things in common. What did I do here? Erase my. All these things have some properties in common, all of these functions. This time, it's the reverse of what we had before. On the exponential functions, remember our exponentials, they were either growing or decaying, looking like one of those two. We said the domain would be infinite. We could plug in whatever we wanted for x and get a y value back out. The graphs went left and right forever. And then the range was from 0 and then up to positive infinity. Well, the reverse is happening here. Now we have a restricted domain but an infinite range. We have graphs that go up and down forever, so everything from negative infinity to infinity here, but we have a domain that's capped at 0. Those x values are not going to be able to get to 0, they can be anything bigger. So from 0 to infinity. And then with the exponentials, we saw a y-intercept at 1 and no x-intercept. Well, the reverse happens here. There will not be a y-intercept for these graphs, and there was an x-intercept at 1, 0. And then instead of a horizontal asymptote at 0, this is going to be a vertical asymptote at 0. Vertical asymptote, and this will be specifically at x equals 0, which is the y-axis. And then when b was bigger than 1, that's the log base 2 or log base 3, we call that an increasing graph. And because those graphs were increasing, we call it logarithmic growth. And when the base is between 0 and 1, like the base of 1/2, then the graph was decreasing. And we would call that logarithmic decay. So very similar to what we saw before. Just everything happening in the other direction, okay? And now transformation rules still apply. So the characteristics that we wrote down here, those are true for like the parent form, where you have the log with a base of x, but nothing else being added or subtracted or multiplied. Now, when we, let's say, shift everything up, it's gonna move things around, or shift everything left or right, things will move. We could also stretch or compress or reflect, but if you have a parent version of a log function, these properties will be true. Okay? Why do I keep doing that? Erasing. All right, so transformation rules still apply. We're going to be looking at a standard form of y equals, oh, I shouldn't have used a here. This should have been an x. So sorry. Log base b of x. We have a times the log base b of x. And then I need to fit more in there. We have x. It's possible we subtract something there. And then afterward we add. So we could stretch, compress, or reflect the graph depending on the value of a. So if it's bigger than 1, it's going to stretch it. If it's a fraction, it's going to compress it. And if there's a negative there, it's going to reflect it. And then h is going to tell us whether or not that graph is going to shift to the left or right. And then k is going to tell us whether that graph is going to shift up or down. Okay, so same transformation rules we've looked at from the beginning of the semester apply. So here, for example, if we were going to compare to log base 2 of x, then we also put in this minus 3 and this plus 1, what would happen to that graph? Well, the minus 3 would make the graph go to the left 3, and the plus 1 would make the graph shift up 1. Here we've got a negative and we've got that 3. So the negative would make the graph reflect over the x-axis, and then the 3 would be a vertical stretch of the graph. And then we can see on this last one, a 1/2 here and a negative in there. So the 1/2 would be a vertical compression of the graph. And the negative that's inside with the x is going to be a reflection over the y-axis. Reflect over the y-axis. Okay, same transformation rules. And then hopefully you could use those in reverse. So if I said take y equals log base 2 of x, shift it left 2, down 3, reflect it over the x-axis, and then stretch it by a factor of 4, then we would have y equal to, let's see, if we were going to stretch by a factor of 4 and reflect over the x-axis, then we would have a negative 4 in front for a, and we would still have our log base b of x. And then if we're going to go to the left 2, we're going to have to put a plus 2 in there. And then if we want to go down 3, we're going to have to put a minus 3 afterward. And all of that could be confirmed with Desmos, okay? So same transformation rules we've talked about. Now, here's sort of the bigger picture. Now we saw some connections between logs and exponentials, but I want to make sure to bring this full circle and hopefully help you remember what we saw earlier in the semester. Let's look at these two functions. So I graphed the log base 4 of x and 4 to the x power. I graphed the exponential function. So g of x is the exponential function with a base of 4. It looks like the exponential functions that we graphed the other day. And then I also graphed the log function, so the log with a base of 4, and then it looks like what we just saw a second ago, okay? So these two graphs, how do they compare? What's happening? Well, the shape is similar, right? But we saw things reverse. So with our log base 4, we had a domain with the log base 4. We have a domain that's restricted from 0 to infinity, and a range that was infinite, the graph going up and down forever. Whereas with the exponential, I'm gonna have to change this color because I want these to coordinate. So sorry. Let's see. Let's make this pink. Okay, with the exponential that we saw the other day, we saw the unrestricted domain, and then we saw the range that was capped from 0 to infinity. And then over here, with the log function, we said no y-intercept and x-intercept at 1. And then with the exponentials that we saw the other day, that was flipped. We said we weren't going to cross the x-axis, but we'd cross the y-axis at 1. So 0, 1 there, and then none there. And the asymptotes were flipped as well. With the log function, we had an asymptote at x equals 0, and then that was a vertical. And then here, with the exponential function, we said it was going to be an asymptote at y equals 0, which is horizontal. Okay, all those things are reversed. Now, I don't know if you remember when things are reversed, when those, but really what's happening is like the x and y intercept are reversed, that's x's and y's. The domain and range are reversed, those are x's and y's. I don't know if this looks familiar, but let me take it back to something, to connect to something we've done before. So remember finding the inverse of a function? If I said to find the inverse of, let's say, 2x plus 1, what did we do to find the inverse of this linear function? Well, we said solve it for x. So if I was to solve this for x, I would subtract the 1 over, I would divide the 2 over, and now I would see my inverse operations undone in the correct order. So I would solve it for x, but it still didn't quite look right. After we solved for x, we said let's switch the x and the y, and then we could call that the inverse, right? Well, let's look what's happening with our log function here. If we have the log base 4 of x, that's what we did a second ago. If I said to take that function and solve it for x, what would you do? If you were solving this for x, you could just rewrite it in exponential form. In exponential form, this would be 4 to the y power equals x. And there it is. X is solved for, right? So these two things are equivalent, right? They're just rewritten. But if we take it one more step now and switch the x and the y, switch x and y like we did with our when we're finding the inverse, right after we solve, if we switch, then we get 4 to the x power equals y. That is the exponential function with the same base. That's what we just graphed on our note sheet. So if we have a log with a base 4 and an exponential with a base 4, right, and there's no other transformations in there, or they had the same transformations happening, those two functions are inverses. Okay, they're inverses. All the x's and y's were switched. And remember, that's how we verified. So if I said plugging 2 in here would produce a 5, then over here plugging 5 in would produce a 2. That's what's happening here. All the x's and y's were switched. So you need to understand that exponential and log functions, they are inverses. That is when they have the same base and the same, h and k that, so they're both, log base 4, exponential base 4. So exponential and log functions are inverses of each other. Now, if we had y equals the log base b of x, that is equivalent to, if we were to write that in its equivalent form, this would be equivalent to b to the y power equals x, but that is the inverse of, if we switch the x and the y, b to the x power equals y. So that log function is equivalent to this exponential, but if you switch the x and the y, you get its inverse function. Okay, so the inverse and the log that have the same base, or the log and the exponential that have the same base, will always be inverses. So for any exponential function, if you have f of x equals b to the x, its inverse will be the log base b of x. So again, if you had, let's say, f of x equal to 5 to the x, then its inverse is going to be the log base 5 of x. Okay, or if it was 3 to the x, log base 3 of x, those two would be inverses every single time. Okay, and that is it. That is it. That is it. I know that was a short one. Let's save the best for last, I guess. So make sure you guys are working on those practices. Remember, they're all going to be due